and we're here today to talk about testing data pipelines at scale. Specifically, I'm going to talk about Spark data pipelines. Maybe show of hands quickly. I'm going to look here. Anybody here used Spark before? One. Okay. Okay, good. They want to see a little bit more. Okay. Fantastic. Okay. You have some. Okay, thank you. So we'll talk about that as well. Great. But I am hoping that a lot of us here are familiar with data pipelines. Data pipelines is basically the idea of taking raw data and creating data sets out of it, right? And that can be for many different use cases. It addresses a wide different use cases. This can be for just data engineering, classic use cases like creating the data sets to work with, or it can be pre-processing, preparing for experimentation, model training, things of that nature. The idea of taking your data sets and running transformation on them. And we're here to talk about what's the best way to test the transformation, the ETLs of those of that data. And a little bit about me again. You already thank you for the very generous introduction. But in a second, in 5 seconds, I've been doing this for a while. Started in 1998, and I've been doing a lot of different roles, mostly for startups. The last 3 startups are Optier, that was sold to SAP, Turbonomic, that was sold to IBM for close to $2 billion, and lakeFS is the current startup that I'm part of. Early stage startup, a lot of fun. I know that there might be folks here that been on the previous call. Was anybody here on the previous call and is familiar with lakeFS? If you can raise your hand, that would be great, so I know how much to talk about this. Almost no one. Okay, great. So I'll talk about that. So I guess just in a very high level comment, like anything that we need to do, we need to test it. And specifically, when it comes to ETLs, it needs to be more than just basic testing. I'm not going to go into the concepts of testing and different types of testings, whether that's integration testing or other things, but it's obvious that if I'm going to write, for example, some sort of data transformation, that a part of the transformation is also going to delete some data, I need to be able to test it in isolation without negatively impacting the rest of the people using the same data sets that I'm working on. For example, in the world of data, or big data specifically, scale makes a big difference also, right? It's very common for companies to need to run some sort of ETLs that need to finish, for example, overnight, right? I'm creating some sort of risk analysis, and I need this to run nightly and create a new data set for my consumers to work on, right? So if I write something and test it against 1 million rows, but it actually runs in production nightly against 1 billion rows, then I just did the basic unit testing, and I didn't do the testing that I actually need. So testing is very important. And today we're going to talk about the ability to create testing environments for data with zero-copy clone. Any questions so far? Okay, fantastic. So let's talk a little bit about how this is typically done today. And obviously, for the sake of transparency, like I mentioned before, I work for lakeFS. lakeFS is an open source solution, meaning a free solution that anybody can use. So obviously, whatever it is that I'm going to present also talks about problems that lakeFS solves, but we're talking about that in the context of other common issues that people have, and we're going to learn things in reference to that. So developing ETL pipelines today. typically what people will do is they will start with some sort of data set that they need to work on, and then they will either sample data or copy data out of that. What do I mean? I need to work with a subset of the data, for example. So I'm going to subset, I need to develop something, and I can't develop against my entire production data. So I'm going to sample part of the data and bring it over to me. Obviously, the dangers of just using a sample of the production data is that you might not test all the edge cases, that you might not test the, like we said, the scale of big data that you want to do. Then you will take your ETLs that you're developing and you point them to your private bucket where you sample the data, and you will experiment, you'll run multiple runs, and when you're done, you will point your ETL to production and hope that everything is gonna work in production. So this is a manual kind of process that we typically go through. It's almost inevitable. And of course, the longer things take, the more chances of things to fail, the data to not be accurate anymore. I might be now working with a data set that's already outdated, and there's a lot of risks associated with that. And it's not uncommon that this takes so long that we actually at some point need to start from the beginning. So I want to walk you through what lakeFS does. So I'll start with the fact that we are working on top of object storages, specifically data lakes that run on top of object store. Who here is familiar? Again, if you can raise your hands, if people are familiar with object stores in general, like S3, Azure Blob, Google Storage, MinIO. Okay, see a couple, I see a few. Okay, so again, this is unrelated to lakeFS, right? There is a concept in the world today of using data lakes. Data lakes, the common architecture of a data lake is that you have some sort of an object storage, such as AWS S3, Azure Blob Storage, Google Cloud Storage. These are all cloud vendors' object storage, but there's also a lot of object store which is cloud agnostic and or can even run on-prem. A lot of storage manufacturers have different object stores like MinIO, Dell ECS, NetApp Storage Grid, and there's a lot more, right? The idea with an object store is that A, it is very inexpensive, meaning you can store massive amounts of data on it, and B, it has incredibly high throughput. So you can basically dump a lot of data onto an S3 bucket all day long for low cost at very big scale, at big data scale, right? So that's typically where data, so that's the architecture of data lake. Typically you have a data that is either being streamed or regularly copied to your S3 bucket, for example. And then you will have ETLs that basically take the raw data and transform it into data sets that will be consumed by other people or systems. So that's a little bit about data lakes in general. We work on top of data lakes because we believe that data lakes have operational challenges. For example, like we mentioned before, I have massive amounts of data, the example that we're talking about today, and I want to develop some sort of transformation around that data, and I want to do this in isolation. Now, luckily, there is something in the world that was already developed to do this for code, GitHub, Git. I'm guessing that most of us here are familiar with Git. So what we said is, let's take something that sits on top of the object store and gives it Git capabilities. So imagine that you can take a bucket or a collection of buckets, and you can give them a Git interface. So I can take my data, my data lake, and I can branch it, just like I will do for code. I can make changes and commit those changes. If I'm not happy with those changes, I can roll back, right? Revert, just like I will do with code again. And then the ecosystem of tools that we have running in our environment can access the data through the lakeFS API and get those versioning capabilities. Now, this is how you will typically access a S3 bucket, for example, you will go to a collection that's within a bucket. With lakeFS, we'll basically include the name of a branch or a commit identifier. And name of a branch will be prod, test, dev, right? Testing 1, testing 2. A commit identifier will be something like production yesterday at 5 p.m. before an ETL ran, or production yesterday at 10 p.m. after an ETL finished. Okay? And then the Git actions themselves, we can run them, for example, within a notebook, or in a web interface, or in a command line interface, like a lakeCTL command, or with SDKs, APIs, clients, things like that. I'll pause here and see if there's any questions. Okay. Another element to be familiar with, again, this is unrelated to lakeFS, this is just in general. Another element to be familiar with is that object stores are immutable, right? That means that if I have a bunch of files that are sitting inside of my bucket, let's say this is my S3 bucket and I have here some files. If I want to modify a file, when I use an object store, I can't, you know, like I can't do what I can do in my file system, which is just open a file, edit it, and save it. What I actually do is I write a new version of that file, right? That's the trade-off. Like we said, it's very inexpensive and it has a huge throughput, but it is immutable, right? What this the approach that we took is we said, let's take advantage of this property, and we're going to do copy and write. And basically, every commit in lakeFS is going to be a collection of pointers to objects that sit on top of the managed bucket. And when a new file is created, again, using copy and write, the next commit will point to that additional file. But files that did not change, like these 3 files over here, you will have multiple commits pointing to the same physical objects. Why is this so powerful? Because let's say I want to create a testing environment. Creating a branch is a metadata-only operation. I'm pointing to the same physical objects as I did before. This means that A, it's highly performant. So if I want to test, if I want to create a copy of my entire 200 petabyte data lake, I can do that without actually physically copying any file, which means that it's highly performant. It's going to take milliseconds, and it saves a lot in storage, right? Because every data scientist, every data engineer, every experiment can have their own branch of the entire data set without ever copying a single file. We actually are saving in storage in 2 dimensions. One is this multiple environment dimension, which you can have hundreds or thousands of those. The other one is in the time dimension. By nature, a lot of times the data lakes, the way that they are, is that you have a big chunk of files that are static files, and then a smaller subset of files that are added and removed on a regular basis, right? So that means that if I wanted to take snapshots and be able to go back in time, right, I will need to take snapshots of the same files over and over and over again. While here, what we actually do is we de facto deduplicate the object store over time, so we can go back in time without taking snapshots of the same files over and over again. Okay, so let's examine a better way to operate. And the idea of this session is for this to be a very workshop, hands-on section. So what I'm going to do is I'm going to start this demo from scratch. I'm going to delete whatever it is that I have in my environment running right now. And I'll show everybody here how we can do this. Oh, I think I already have deleted everything. Sorry. Show everybody here how we can work with lakeFS Here we go. Let me delete this. From scratch, and this will build an environment. It's going to have Spark in it, and going to have lakeFS in it, and it's going to be a great way to kind of get hands-on with some generic data engineering concepts. Okay, so I'm going to utilize, like I mentioned before, lakeFS is an open source project. So all our code is online. I'm going to use the company behind lakeFS is a company called Reverse. I'm going to utilize a project out of Reverse called lakeFS Samples, right? This is a set of samples that you can use to learn lakeFS specifically, but in general, it has a lot of different examples of different use cases that you can use. The only prerequisite for this is that you should be able to run Docker locally on your environment, and in order to run these sessions. So I'm gonna, what I'm gonna do is, again, I'm gonna really start from scratch. I'm gonna delete anything that I have here. Is this okay? Can you guys see my, is this big enough to read? Can you guys read my? Anybody hands up if you can read my thing and see chat? Yes, perfect, thank you. Excellent. So this, I'm gonna put here in the chat where I'm at, so everybody can do this side by side with me if you want, right? So this is lakeFS samples. There are two ways to run lakeFS samples. One way is to spin up just a Jupyter notebook that we can connect to a lakeFS server, an object store, and so on. If you already have a data lake, this probably makes sense. I'm going to guess that the vast majority of us here today don't have a data lake. So we're going to run with the optional way that will spin everything up for us. So this is going to spin a Spark UI for us, a notebook server, a Jupyter notebook, Min.io. Min.io is an open source object storage solution, and lakeFS. And we're going to do all of this in a single command, just to give us a way to get started. So the first thing that I'm going to do is I'm going to clone this repo and then go to that directory. So let's start with that. Git clone, and this will go and copy everything. By the way, for me, building this for the first time will probably take just a few seconds. Unfortunately, for those of you doing this for the first time, there is a good chance that this will take significantly longer, right? It can take 20, 30 minutes, depending of how many prerequisites of other libraries you have. Those of you who have not used Docker before, or are relatively new to it, just that if there's a lot of dependencies, it might take some time to build these samples. So I copied everything here. So I have my lakeFS samples. And now what I'm going to do is I'm going to build my sample. I'm going to use the Docker Compose. And as I mentioned before, I'm going to use this local lakeFS profile, which basically will spin up for me not only lakeFS, but also an object store, Min.io in our case, that we can work with. And not only the Jupyter notebook, but the entire system that we can work with. So I'm going to run this. Again, for me, this will take just a few seconds, because I have all the prerequisites and everything is up and running. It might take a little bit more for you, but let's see what I have here. And again, this is a great environment for you, for anybody that's interested in learning about this to get started, because I have here a Min.io UI. Again, Min.io is an object storage you guys can learn to use. So I'm going to go to Min.io. Okay. And I think it's Min.io admin, if I'm not mistaken. It's written here anyway. Okay. So I have here a Min.io environment, and I have here 3 buckets. I have an example bucket, a quick start REPL, and a sample data bucket. And these have all different files in them. So this is my dataset, my object store, right? So I have that. I have a Jupyter notebook. Let's go to our Jupyter notebook. when I go to my Jupyter notebook here, I'm going to have an index notebook that you can go to. And this is where this starts getting interesting, because we have here a lot of different examples that everybody can use. So integration with Spark and Python, creating test dev environment with lakeFS branches, data lineage, delta lakes, delta tables, Flink, machine learning experimentation, multi-buckets, kind of like those of you who are familiar with like the medallion architecture. There's really a lot of examples here. So just by doing this, you now have a wide variety of examples that you can use to learn not only lakeFS, but generally to see examples of how things work with different technologies that you can work with. So, and the last thing that we have here is we, of course, have the lakeFS UI. So it goes, this is lakeFS. I have here one repository called the Quick Start repository. If you're interested, you can also follow the instructions of the Quick Start repository and work that way. But what we're going to do today is we're going to go through the notebook. So the notebook will walk, and I went to the Spark demo, which is the first demo over here. We're going to do basics today, right? So anybody here who has yet to use notebooks like this? Should I review some of the... Okay, it looks like everybody's familiar. Okay, great. So in general, these notebooks are a very common way for data scientists, data engineers to work against the data. The idea that it works is that you have these different, let's say, sections which we can run independently. Unlike code, this doesn't necessarily run from start to finish. So I can go and I can run either by clicking play any individual box that I'm standing on, or there's a shortcut that's almost always the shortcut, which is Shift Enter, and I can go back and forth and play with data. So this is a very common way for folks to interact with data. Again, either for machine learning experimentations, for data pre-processing, and so on and so forth. It happens to be that all the parameters for this are already set up in advance for you. So if you ran which we have, right, the local lakeFS profile, then there's nothing that we need to change here. If we haven't, and you have a lakeFS server somewhere else, then you want to put here the link to your lakeFS server. Or you want to put here the link to your bucket, your AWS or Azure or whatever bucket that you're using, depending on how you use lakeFS. So what I'm going to do here is I'm going to configure my lakeFS endpoint, which is my local server, as we saw, this guy over here that I have running, and and a namespace, which is example, and we're going to give a repository name, Spark demo. A repository is a logical term, so it's a group of data sets that work together completely within us. We're going to create the entire thing from start to finish. And here I'm going to work with a lakeFS client. I'm just creating a client and using those configurations. So this is a way for me to connect with this lakeFS server that we spoke about before. And now I'm going to create a repository. So I'm going to check if, and again, the code is all here already ready. I'm going to create this Spark demo repository. So let's do that. So now when I go here to lakeFS, if I refresh the page, then I will see this new repository that we just created called Spark demo. The repository is sitting on a namespace, S3 example Spark demo. We can see that namespace in the object store as well, right? In our MinIO object store. It's right now empty, has no data in it, but we just created our first repository. The next thing that I'm going to do is I'm going to set up a Spark. So I'm creating a Spark session here just see that this will output the version of the Spark by running this command at the end. So I'm creating the Spark session. So now we have Spark session, and let's start using this thing. So I'm gonna some parameters here that I'm going to set, like the source branch, the new path, the file name. We'll see this soon why this is important. And we're going to upload the file. This file sits inside inside my, actually, I think this file sits here in data. We're going to upload this file, lakeFS test.csv, into my lakeFS source branch, into my repository ID. So right now, like we said, this is empty. Then I'm going to go and I'm going to upload files into this. Okay. So let's refresh this. Paragraph file, it's called lakeFS test.csv. This is a 5 columns file. It's the content of the file doesn't really matter, right? It's 1, 2, 3, 4, 5. That's what it is. It's a CSV file that has 1 to 5 in it. I'm assuming that this is pretty straightforward. Now, here is where the Git interface comes into place. I uploaded the file into my main branch of my Spark demo repository. This is an uncommitted change, right? So I added this file, but I did not commit these changes yet, right? Just like we do for code. So the next thing that I'm going to do is I'm going to commit these changes. Here we go. And then if I want to read this file in the future in my notebook, I can create a path, look at the repository, which is Spark demo, at the main branch, right? Source branch is my main branch, or yeah, my main branch, and the file name which we read, and I can just read that file and see what it is. And now I'm going to get, 1, 2, 3, 4, 5, which is the content of this file. So the idea is that now I have a branch with a file, and I can read this branch by accessing a specific branch. Now, let's say that now I want to create a testing environment, right? And my environment. So right now, I have a single branch, my main branch. I'm going to create a new branch. I can create a new branch by going into lakeFS, clicking on branches, and then clicking create branch and create this branch. Or I can create a branch using my Python code. I'm going to use my Python code here. I'm going to go and create a branch in my repository out of main, and I'm going to call this branch, I believe, experiment. That was the name that we gave here, experiment 01. Again, this is the zero copy clone, right? I did this, I created a new branch. Now I can read the data from my experiment branch instead of my main branch, and it's going to look exactly the same. Right, what I did here is I repartitioned the data in my new branch. What does this mean? We have 2 branches, experiment and main. At this point in time, these 2 branches point to the same reference commit. Again, zero copy clone. If I look at the main branch, I only see this lakeFS test.csv. However, I just ran a command right now to repartition the data by a specific column in my new branch. This means that now, when you look at the experiment branch, I added a new type of data, partition data, and the partition data accordingly. So this data is only done, this change was only done in my specific branch. Now I can commit this change, right? So what I actually did here, what we saw happen right now, is that we took the data set out of main, we created an experiment branch, and now I'm developing against it and I'm testing against it, and I can commit those changes. And the last thing kind of to show you is that now after I committed these changes, I have 2 branches that are no longer pointing to the same reference commit, and I can compare these two, and I can promote all the changes from my experiment branch to the main branch and atomically make these changes. The reason that's important is that imagine that your ETL changes 20 tables and not one table. And you want to make all these changes atomically in one atomic action. That's something that you can do here as well. I see a question, so let me make sure I ask the question. Does lakeFS recognize a story sequence that can commit to be shared across branches without conflicts? Really, really great questions. So yes, lakeFS does organize historic sequences, and commits can be shared across branches without conflicts. Well, if there is no conflict, I'll explain. So, for example, let's play this game to answer this question. Now I have here two branches, experiment 1 and main. Okay, experiment 1 is ahead. We make these changes. I can already go to the commits in experiment 1, and I can see this is the current commit that we're on, right? These are the files that change a part of this commit, just this CSV. But I can also go to the parent commit and see what that parent commit looked like. And I can even browse the data, not in a specific commit ID, right? I'm no longer looking at the branch, I'm looking at the commit identifier right now, and see what the data set looked like at that point. Even if I go ahead and merge, right? If I compare experiment 1 and main, I can merge the data just for the sake of this example. And now there's also a question about what to do if there's a conflict. So what happens if the same data is changed in more than one place, right? Do I want the source win? Do I want the destination to win? Or do I want to just fail the merge? And I'm going to use fail merge, right? So now after I did this, promoted the data, that means that when I go and look at my main branch, right, now I'm also going to see the partition data. But once again, to answer your question about the sequence, if I go to the commits now, I can see also the merge, right? What happened here is that we merge experiment 1 into main, and these are the files that changed as part of it. And you see that I answered everything on this question. Can commits be shared across branches? Yeah. So another interesting thing is that, let's say that there's a lot of data engineering tasks like backfilling, reprocessing, troubleshooting all data sets. Like there's a lot of reasons to go to historical points in time. So if I go here and I'm in main and I want to look at something historically and I want to create my new branch, so I can go and create a branch, but I'm going to troubleshoot. I'm going to troubleshoot and an old issue. And now I'm not going to branch out of a specific branch. I'm actually going to branch out of a specific commit identifier, right? So I'm going to create a copy of the data, right? This is zero copy clone of the data as it was in a specific point in time, right before I repartitioned the data. So now if I want to rerun my code and test it against this, I can do this also against this. And again, at the risk of sounding like a broken record, in a very high performance without actually copying any files. Okay, I hope I answered that question. Just a few other things to kind of talk about. So again, I think what we showed here is that next time I don't need to go through all these changes. I can just branch something, develop it, and then merge it if I wanted to. The outcomes of using something like this is that you get tremendous amount of storage savings. You get the ability to deliver things much, much faster to the market, but we also reduce the risk. So if something bad happens to production, today is it's a manual, heavy lifting, labor-intensive, time-consuming process to try and recover data on a data lake level, and this is the way to do this in milliseconds. It's worth mentioning, like I mentioned a few times over here, that everything that you saw today is open source free. You can use it. We have an open core approach, meaning that there's no artificial boundaries with lakeFS. You can use this at scale with petabytes of lakes with no issue. we of course do have some enterprise features as well that are available either on-prem or on cloud services. So the only things that I will share here is that we also have a really, really tremendous Slack community. Would love to see some of you join that. lakeFS.io/Slack will take you there. We have, sorry, I'm looking for a better slide for this, because we have a bunch of them. Sorry, so we're fortunate to have, sorry, I'm getting the slide from previous call because I think that was better. No, I can't find it. Okay, we have a really incredible community on Slack. If you go to lakeFS.io/Slack, you can raise it. It's a great place to ask questions. These samples are available for you, as you saw before, and that's a great resource for you to play with open source solutions in general, like Min.io, like Delta tables, like Airflow, like Prefect, like Dagster, like there's really Labelbox. There's really a lot of examples over there. Would love to see you, and I'm here if there's any last minute questions. Going once, going twice. Okay, thank you everybody. This was really a lot of fun, and hope this was productive for everybody. Have a wonderful day. So the notebooks are shared. So for the questions, for the questions about this, the notebooks are all available right here, and this is free for use, and you can follow the instructions over there. Thanks everyone. Oh, I see support. Okay, support for MS Data. Support for MS Data. We definitely have support for Microsoft Data, Factory, Azure Blob, and generally anything that has the ability to expose an endpoint of a bucket, which Data Factory has it. I need good videos to understand unit testing and integration testing on pipelines. Can you provide any? Yes, if you're looking for videos, we have, let me find you something on the fly. Used before. So maybe this can be helpful. Oh, no, I sent the wrong thing. Sorry. I sent you the wrong thing. Maybe this can be helpful for you, Elandra, as an example of a video. Going over this. Awesome. Great questions. Any other questions? Okay, awesome. Thank you, everybody. Have a wonderful day. Thank you. Goodbye.